This is a video on solving a system of linear equations graphically. The first thing to talk about is just making sure you understand what I mean when I say a system of linear equations. So I'm really talking about, looking at where two lines might cross and trying to figure out where they intersect. So the solution to a system of equations are the points where the graphs, I should say, of the equations intersect. So you're trying to find the point where the two lines cross. Now, later on in other courses, you might learn about different types of graphs. So that's why I kept it kind of general and said the solution is where the graphs intersect instead of the lines intersect. But in our case, we're looking for where the lines intersect. So let's take a look at just an example. We'll say determine which of the following ordered pairs is a solution to the system. And I'm going to give you a system of equations. First one I'll call y equals 3x minus 2. And the second one 5x minus 2y equals 2. So I'm giving you these. I'm going to label them as equation 1 and equation 2, just using Roman numerals, just so I can talk about them. So I haven't actually given you the entire question yet. So the first thing, right, so determine which of the following ordered pairs. So I'm really trying to figure out the point where these two lines cross. So it's an ordered pair, and I want to see, for this first one, I'll just call it example A, is this a solution? Now the way you determine if it's a solution or not is you want to make sure it's a point on the first line and it's also a point on the second line. Because if it's a point that's on both of the lines, that means that the ordered pair is a solution. If the point only falls on one line, then it's not a solution, right? So for these to intersect, the point has to be on both lines. So basically you're doing like a check almost, right? So I'm going to do a check. And when I do a check on this, I'm going to sub into, let's say, equation 1 first. For x and y, remember this is x and y for the point. So in equation 1, we'd have y, which is 4, equals 3 times x, which is 2, minus 2. We get 4 equals 3 times 2 is 6 minus 2. Simplifying this, you get 4 equals 4. It checks out. Now, remember, that check only tells you that the point 2 comma 4 is on equation 1, is on the line y equals 3x minus 2. It doesn't tell you it's a solution to the system, because to be a solution to the system, it has to work in both, and we haven't checked the second one yet. So you do have to check in both equations. So checking in equation 2, we had 5 times x, so it'll be 5 times 2, minus 2 times y, so 2 times 4. We're going to check, does that equal 2? Well, 5 times 2, that's 10, minus 2 times 4, that's 8. Does that equal 2? 10 minus 8, yeah, 2 equals 2. So it checks out. So since it works in both, then we can say, yes, all right, 2 comma 4 is a solution to the system. That's what's important to make sure you know that the reason it's a solution is that it works in both. Let's look at, I use the same equations I have above, these two, y equals 3x minus 2 and 5x minus 2y equals 2. And we want to find if 3, 7 has a solution to the system. Well, remember what we're doing. We're checking here. So checking in the first one, we had y equals 3x minus 2. Or this is x, this is y. So if y equals 3x minus 2, let's write it here so it's easier to see. All right, this is equation 1. Then we would have 7 equals 3 times 3 minus 2. So 7 equals 9 minus 2, so 7 equals 7. It checks out. All I know so far is that the point is on line 1. But now we also have to check on line 2. Line 2 was 5x minus 2y equals 2. And we're just substituting in, so it'd be 5 times 3 minus 2 times 7. Well, does that equal 2? Well, 5 times 3 is 15, minus 2 times 7 is 14. Does that equal 2? Well, it doesn't, right? You got 1 equals 2, so that's not true. So that tells me that the point 3 comma 7 is not on line 2, right? It's not on the 5x minus 2y equals 2. So since it doesn't fall on both lines, we can say no, 3 comma 7 is not a solution to the system. Because what we've shown is that it falls on line 1, but it doesn't fall on line 2. So it's only a point on line 1 is all we know from that. Alright, so when you are looking at a system of equations, if we have two linear equations, 2 lines, you really have 3 possibilities. Alright, so when 2 lines are graphed, we have 3 possibilities. Now, the possibilities are one that we've kind of already talked about. Alright, so the first possibility is that the lines intersect. At a point. So if they intersect at a single point, just a quick little sketch of an x and y axis here. Here's the x-axis, here's the y-axis. We'll have one line that might look like that. And we'll have another line that maybe looks like that. So we got these 2 lines. The solution, remember, is where they intersect. So that point right there. So that's your solution. And in this case, if they intersect like that, there's exactly one solution. The lines are not going to intersect again. You might hear this being called a consistent graph or a consistent solution. It's okay to know that information. Really, the key thing here, though, is I want to make sure you know it's exactly one solution. Alright, so the lines could cross at one single point. Now, the other possibilities that could happen are, a little more, so that's the 2 graphs cross at a point. The other possibilities that could happen are that the lines are parallel. Now if the lines are parallel, think about what that means. So let's draw just a quick sketch. Of an x and y axis. There's the first line. There's the second line next to it. They're parallel. Well, remember what I said about the solutions. The solutions to a system are where the lines cross. If these lines are parallel, you got to make sure you realize they never cross, they never intersect. If the lines never intersect, then what's the answer? Well, that means that there's no solution. Because remember, the solution is the point where the two lines cross. If the lines never cross, then there is no solution. You might hear this called inconsistent. Alright, so the possibility so far that the lines intersect at a single point, the lines are parallel, or the third possibility is that the lines are the same. So if the lines are the same, and it might not be obvious to you if you look at the equations, at least not at first, that the lines are the same. You know, here's x, here's y axis. You have line 1, you know, maybe it looks like that. And you have line 2, and it's going to be right on top of it. Alright, so those lines are the same line. If the lines are the same, then let's talk about where they intersect. Well, all the points on the first line are the same as those on the second line. So they perfectly overlap with each other. So this means that all points on line 1 are also on line 2, which means that, you know, there's an infinite number of points that are on each line, so there's infinitely many solutions. So this means there are infinitely many solutions. Or you could say an infinite number of solutions. What you can't say is, don't say infinity. That's not the same thing. And it's not every point in the world. It's not all real numbers or anything like that, because it's only the points specifically that are on one line that are also on the other line. Right? Points that are not on either line don't become solutions to the system. Sometimes you might hear this called dependent. So when we're graphing a system of equations, right, we have three possibilities if they're both linear equations. They intersect at a point, and therefore there's one solution. They're parallel, so they never intersect, which means there's no solution, or they're the exact same line, so they overlap right on top of each other, and there's infinitely many solutions. All the points on the first line are also on the second line. Let's take a look at some examples that use this. So for this example, remember the directions here are going to say solve the system graphically, which means it wants you to graph the lines. What it doesn't mean is, it doesn't mean do it algebraically, which is what we're going to do in the next few sections. So graphically means that they want you to actually graph the lines. So the first line we have x plus y equals -1. I'll label this equation 1. And the second one we have is y equals 2x minus 7. I'll label this equation 2. And now to graph the lines, the easiest thing to do first is that we are going to try to get both lines into the y equals mx plus b form, because that's the easiest way to graph. You could graph them in other ways if you know other ways of graphing, but for equation 1, if I have x plus y equals negative 1, right, that's what I had originally. I want to get this into y equals mx plus b form. I'm going to subtract x from each side. So you get y equals negative x minus 1. Remember, they're not like terms. Keep the sign with the term. And remember, y equals mx plus b form is called the slope-intercept form because it gives you information. Right? The slope, right, is whatever is in front of x. In this case, m, which is the slope, is equal to negative 1. The negative 1 at the end here, this is the y-intercept. Remember, b always gives you the y-intercept. So the y-intercept is always 0, comma, whatever b is, so 0, comma, negative 1. So for this first line, I know the slope and the y-intercept, and I want to graph it. Now, graphing this, and I'll do it here in red, keep in mind that you always start with the point you know, right, which is the 0, negative 1. So 0, negative 1 would be right there. The slope is negative 1, so the slope, remember, as a fraction would be negative 1 over 1. And this gives you directions on how to move from your y-intercept to the next point. This will tell you to go down 1 unit, and this says to go right 1 unit. So from this point here, I want to go down 1 into the right 1, down 1 to the right 1, down 1 to the right 1. Now you only really have to do it, so you have 2 points to graph a line. The reason I'm doing it with several more points is because then it'll make our graph more accurate. So drawing that line straight through there, and this is equation 1. Now we'll take a look at equation 2. Equation 2, we have y equals 2x minus 7. To graph that, we already have the y equals mx plus b form, so you really can just pull the information you need immediately from it. The slope, remember, is whatever's in front of x, so in this case is 2. In the previous one, you see a negative here. Remember, that negative really means there's a negative 1. That's why we chose negative 1. Here it's 2, so whatever's in front of x is 2. The y-intercept, remember how you get it. It's 0, comma, whatever b is. So 0, comma, negative 7. So when I go to plot this, right, and I'll use green for this one, right, we start at 0, negative 7. So 0, negative 1, 2, 3, 4, 5, 6, negative 7 would be here. And the slope equal to 2 tells me, as a fraction, that's 2 over 1. So how does that tell me to move around? Well, it says you want to go up 2 to the right 1. So from this point, we're going to go up 1, 2 to the right 1. And now, to be more accurate, I'm going to do a couple more points. Go up 2 to the right 1, go up 2 to the right 1, and then we'll draw our line through there. That is line 2. Now don't just stop here, right? So we're trying to solve the system. Remember, solving the system means I want to find the point where they intersect. So in this case, where do they intersect? Well, they intersect at this point right here. And that's what you're really looking for, right? When you go to write the solution is an ordered pair. Every single time you have a system of equations with 2 variables. So the solution here we have is the x value, which is 1, 2. And the y value is negative 3, so the solution here would be 2, negative 3. And that would be the answer. So, making sure that you graph both lines, make sure you're being very accurate, is really important here because you want to find that point where they intersect. And if you're not being accurate with your lines, then you're not going to actually find the correct point. Let's take a look at another one. Okay, so the next example we'll look at, again, the directions will say solve the system graphically. Graphically is important there because it means you want to draw both lines, or graph both lines. And the first equation, x plus y equals 4, that's equation 1. And the second equation, I'll say, is 2x plus 2y equals 0, which I'll label equation 2. And you want to do the same thing with what we did last time, which is try to get both lines in the y equals mx plus b form, so then it's easier to graph it. So let's take a look. If I have x plus y equals 4, right? This is equation 1. Then to get y equals mx plus b form, all I'm doing is subtracting x from each side. So I end up with y equals negative x, that's a positive 4, so plus 4. Once you have that, you know, you've got the slope-intercept form. You can pull the slope and the y-intercept right from that, right? So slope, m, is what? Well, it's equal to whatever's in front of x. In this case, it's a negative 1. Right? And what's the y-intercept? Well, the y-intercept comes from whatever b is, right, in the slope-intercept form. So it's 0, comma, positive 4. So if I wanted to graph this, right, we're going to do what we did before. We're going to plot the y-intercept. So 0, 4. Right, so 0, 1, 2, 3, 4 would be right there. And then you want to use your slope to move around from that point. Well, negative 1, remember, is the same as negative 1 over 1. So the top number tells you, right, the numerator tells you you're going to go down 1 because it tells you about your change in y. Over the denominator tells you about your change in x, remember, so that tells you you're going to go right 1. So once you have that, starting at the point you have, 0, 4, you're going to go down 1 to the right 1, down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. You could do this the whole way through. And once I have that on there, I'm ready to draw my graph going through that. So this was equation 1. Similarly, for equation 2, I have 2x plus 2y equals 0. And then we're trying to get y by itself again, to get that y equals mx plus b form. So the first thing I'll do here is I will subtract 2x from each side. And you end up with positive 2y equals 0 minus 2x, which would be negative 2x. Now you can put plus 0 here if you want, but typically we don't, because anything plus 0 is just itself. So we're going to leave that. Now we want to solve for y still. So to solve for y, we're going to divide both sides of this by 2. So you get y equals negative 2 over 2, which is negative 1x, or just negative x if you wanted to say that. And then, you know, there is no value here for b, which means the value for b is 0, right? You could write y equals negative 1x plus 0 if you wanted, but typically we don't. So this is just the line y equals negative x. So looking at this, we know that the slope for this line is whatever's in front of x. So the slope is negative 1. The y-intercept, since you don't see a value for b, is actually 0, right? So it's 0, comma 0. It's going to be the origin. So something to point out, even before I go to graph this, is look at what we have here. We have two lines that have the exact same slope, but they have different y-intercepts. So we know they're not the same line, right? They don't have the same equation, but they have the same slope. And if two lines have the same slope, that tells you something. It tells you the lines are parallel. So something to realize, you can find that out right from the slopes there, but we could plot it as well, right? So if I plot 0, 0, and I follow my slope, negative 1, remember that's negative 1 over 1, so that means change in y over change in x means you're going down 1, right, from that point, over 1 to the right, down 1, over 1 to the right, down 1, over 1 to the right. So from there, we're going to draw in our line, going down 1 over 1 to the right on each of those. That's equation 2. Remember, your line should have arrows on the ends because they're going on forever in both directions. And note the lines are parallel, right? So just a couple notes, right? So note same slope but different line, right? Or different y-intercept. Means lines are parallel, so they never cross, which tells us there's no solution. Now, that's me just kind of analyzing what I have here in terms of the slope and the y-intercept, but you really can see it right here on our actual graph, right? If you look at this graph, the graph we have here, these lines are parallel. They don't ever cross. So there is no solution where they cross. So the answer would be no solution. All right, let's take a look at one more. So if I said to solve the system graphically. Okay, graphically means you want to graph them both. The first equation I'll have is y equals 1/2 x plus 1. I'll label this equation 1. The second one is 2y equals x plus 2. And I'll label this equation 2. Now again, the first thing I'll do is try to get the y equals mx plus b form for each of them. For the first one, we already have that slope-intercept form, right? So y equals 1/2 x plus 1. We know the slope is 1/2. We know the y-intercept is 0, comma, whatever b is, so it's 0, comma, 1. And then we plot, right? So the y-intercept is 0, 1, so 0, 1 would be right there. The slope tells us, remember the numerator tells us about moving up or down, so this tells us move up, right, because the change in y. Over the denominator tells us about the change in x, so we're going to go right 2. So from this point, you're going to go up 1 to the right 1, 2. From this point, 1, up 1 to the right 1, 2, up 1 to the right 1, 2, and you could, graph that line through there. We'll label it equation 1. Similar to our previous examples for equation 2, right? We have 2y equals x plus 2. Again, we want to try to get this into the mx plus b form. So we have y here that we need to isolate, so we're going to divide by 2. Remember, I'm dividing by 2 to each term when I do this, right? So you divide each side by 2 to isolate y. End up with y equals, now what's really in front of the x, right? There's really a 1 there, so it's really like 1/2 times x plus 2 divided by 2, which reduces to 1. Well, what do we got? We have y equals 1/2 x plus 1. If you're careful and you're noticing, that was actually the original first equation. So these are going to be the same line, right? You can see it right away. The slope is still 1/2. The y-intercept is still 0, 1. But you can see it, right? So these are the same line. If I was to graph the same line, think about what's going to happen. I'm going to start at 0, 1. I'm using the same slope, right? I'm going to go up 1 to the right 2. Up 1 to the right 2. I'm going to actually draw the line right on top of the other line. So the blue line I'll call equation 2, but they're the same. They're just written in different forms to start. So the same line, when you have the same line, well, where do these intersect? Well, they intersect everywhere for every point on one line that's also on the other line. So we say that there's infinitely many solutions. So You can recognize that right away if there's the same line here, and you could probably tell me if there's infinitely many solutions as soon as you got into the second line of the y equals mx plus b form. But if they ask you to do it graphically, make sure you graph it. So again, there's three possibilities when you graph. Either the lines intersect at a point, the lines are parallel, so there's no solution, or the lines are exactly the same, so there's infinitely many solutions.